Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
I want you to start by just taking a moment to imagine something that completely defies our standard everyday understanding of the cosmos.
Right.
Because, when you look up at the night sky, it feels timeless, it feels static, eternal, really. The constellations you see tonight are, they're the exact same ones the ancient Greeks looked at.
The same ones the Egyptians mapped out, yeah.
Exactly. But right now, I want you to picture a supermassive black hole. And it is sitting in the dark, 1.3 billion light years away from where you are sitting right now.
Which is a distance that's almost impossible for the human brain to process.
It really is.
Yeah.
Just to put that distance into perspective, 1.3 billion years ago, the only life on Earth was microscopic, single-celled organisms floating in the ocean.
Yep.
The light from what we are about to discuss today has been traveling through the absolute void of space for all that time just to reach our telescopes.
Just staggering.
So this black hole is a cosmic engine of unimaginable power. Now imagine that engine seemingly reaching out and just pulling the plug on its own immense power supply.
Plunging into relative darkness.
Right. Only to rapidly flip the switch back on and just roar back to life.
I mean, it sounds like science fiction. You expect stars to twinkle, sure. You might even expect a supernova to flare up and fade away over the course of, say, a few months.
Sure. Things we've observed before.
Right. But a supermassive black hole, the gravitational anchor of an entire galaxy, suddenly throttling down and then powering back up, that completely rewrites our expectations of how these behemoths operate.
Totally.
We are talking about objects that dictate the evolution of billions of stars, suddenly changing their fundamental state.
And we aren't just speaking in hypotheticals today. We are looking at a very specific, very real celestial object. The galaxy cataloged by astronomers is J12242309, though you will also hear it referred to by another astronomical survey designation, which is HE 12372352.
Yes, catchy name, I know.
Right, rolls right off the tongue. But the mission for our conversation today is to truly try and grasp the sheer scale of what it means when an active galactic nucleus, or an AGN, suddenly changes its behavior.
It's a huge paradigm shift.
We are taking those beautiful but, static pictures of space that we all have as our computer backgrounds, and we are stepping into a dynamic, real-time cosmic mystery.
Because for a long time, astrophysics was essentially an observational history science.
Right.
We looked at things that took millions of years to change, so from a human perspective, they looked frozen.
Like a snapshot.
Exactly. But HE 12372252 forces us to look at the universe as a violently active, breathing environment. What we are examining here is a phenomenon known in astrophysics as a changing look, AGN, or a CLAM.
Lazy.
Right. It is a classification that represents some of the most extreme, rapid transformations we have ever witnessed in the centers of galaxies.
So, okay, let's unpack this, because before we can truly understand why this supermassive black hole eventually turned off and shocked the astronomical community, we need to understand what it actually looks like when it is fully on.
Yes, baseline is important here.
We need to understand the anatomy of this cosmic engine. If a black hole, by definition, lets no light escape, how can an active galactic nucleus be the brightest thing in the universe?
Well, to understand a changing look AGN, we have to establish what an active galactic nucleus is at its core. At the heart of most, if not all, large galaxies, including our own Milky Way, by the way, lies a supermassive black hole.
Right. Sagittarius A star for us.
Exactly. And these can be millions or even billions of times the mass of our sun, all crushed into a singularity.
Mind-bending.
It is. But as you pointed out, a black hole by itself is just a massive gravitational sinkhole. It is invisible. It doesn't emit light. What makes an AGN active and incredibly luminous is the material surrounding it and the brutal physics of how that material falls in.
We are talking about gas, dust, maybe stars that wandered a bit too close and got shredded.
Definitely shredded stars, yes.
But this material doesn't just fall straight down like an apple falling from a tree, right?
It can't. And that is due to a fundamental law of physics called the conservation of angular momentum.
Okay. For anyone whose high school physics is a bit rusty, this is the classic ice skater effect, right?
That is the perfect way to visualize it, yeah. When a figure skater is spinning on the ice with their arms outstretched, they rotate at a certain speed.
Okay.
But when they pull their arms in tight to their body, they spin dramatically faster. The angular momentum has to be conserved, so a smaller radius means a higher velocity.
So how does that apply to the black hole?
Well, in space, you have massive clouds of gas and stellar debris caught in the black hole's gravitational pull. Because that material always has some slight initial rotation, nothing is ever perfectly still. As it gets pulled closer and closer to the black hole, it spins faster and faster.
Pulling the arms in.
Exactly.
Yeah.
And the centrifugal force causes this spherical cloud to flatten out into a disk. We call this an accretion disk.
An accretion disk.
Right. It is a rapidly swirling whirlpool of matter, moving at significant fractions of the speed of light.
Wow. And because the material in the inner part of the disk is closer to the black hole, it has to orbit much faster than the material in the outer edge just to keep from falling in.
Yes, Kepler's laws in action.
That speed difference layers moving at different speeds that must create an unimaginable amount of friction.
The friction is the engine. You have adjacent layers of gas scraping against each other at relativistic speeds.
So close to the speed of light.
Exactly. But it is not just physical friction, like, rubbing your hands together. We are dealing with plasma here.
Okay, so gas where the electrons have been stripped from their atoms.
Right, and because it's plasma, that means it is highly magnetized. The magnetic fields within the spinning plasma get twisted, stretched, and then they violently snap back in a process called magnetic reconnection.
Oh, wow.
Yeah, this acts as an incredibly powerful source of viscosity. The sheer mechanical and magnetic stress heats the material in the accretion disk to millions of degrees. It transforms from cold cosmic gas into a blindingly bright, superheated plasma.
So the accretion disk itself is actually glowing.
Radiantly glowing, and there is a halo of even hotter, thinner plasma hovering just above and below the inner disk called the corona.
Like the sun's corona, but way hotter.
Way hotter. The AGN corona reaches temperatures in the billions of degrees.
Billions, that's just wow.
Yeah. Together, the accretion disk and the corona radiate an astonishing amount of energy across the entire electromagnetic spectrum, from radio waves all the way up to high-energy X-rays. That brilliant radiating structure is the active galactic nucleus.
So it's basically a giant power plant.
It is. The engine is so efficient at converting mass into energy that a single AGN can easily outshine the combined light of every single star in its entire host galaxy.
I really want you to hold on to that image if you're listening. A structure around a black hole that is brighter than billions of stars combined. Which brings us to the timescale anomaly.
Yes, the anomaly.
This is the core fact that makes HE 1237-2252-7 so absolutely mind-bending. Usually when we talk about a supermassive black hole going through feeding episodes, periods where it consumes more matter and gets brighter, or consumes less and dims, astronomers expect those changes in luminosity to take tens of thousands or even millions of years.
Right. The physics simply demands time because of the sheer physical size of the objects involved.
They're just too big to change quickly.
Exactly. An accretion disk around a supermassive black hole isn't measured in miles or kilometers. It is measured in light days or light months.
Wait, light months?
Yes. It might take light, traveling 186,000 miles per second, several months just to cross from one side of the disk to the other. So if a process is going to change the overall structure and energy output of something that vast, it is limited by the speed of light and the speed of sound within the plasma. So a human lifetime is a blink of an eye compared to the feeding cycle of an AGN. At least that was the standard assumption across astrophysics.
Wait, so if this disk is measured in light months across, how could it possibly change fast enough for us to notice? I mean, the data for HE 1237-2252 completely shattered that assumption.
Completely shattered it.
Observers didn't watch it dim over a millennium. They watched its X-ray brightness completely collapse, dropping by a staggering factor of 17 in just 18 months.
A factor of 17 drop in 18 months for an object of this magnitude is, well, it's practically a free fall.
Yeah.
It is structural failure on a galactic scale happening in real time.
To put that into perspective for you, it is like going out to your favorite national park to look at a massive, towering mountain range, like the Rockies or the Alps, and watching the largest peak erode into flat dust over a single weekend.
That's a really good way to think about it.
It's a timescale that makes perfect sense for human events, building a house, completing a work project, but it is shockingly, almost impossibly fast for astrophysics.
It really highlights a crucial point about how limited our observational window of the universe really is.
What do you mean?
Well, we have only had X-ray telescopes in orbit for a few decades. Even within that narrow window, this galaxy proved that catastrophic structural changes can happen in a flash.
Which is terrifying and exciting all at once.
Exactly. Now, to picture this properly, we should also clarify the specific type of galaxy we are looking at. HE 1237-2252 is not a quasar. It is a Seyfert galaxy.
Right, and that distinction changes how we actually view it through our telescope.
It does. Both quasars and Seyfert galaxies possess extremely bright, active nuclei powered by supermassive black holes. However, a quasar represents the most extreme end of the spectrum.
The gas guzzlers of the universe.
Yes. It is so unfathomably bright that its light completely washes out the host galaxy surrounding it. When you look at a quasar through a telescope, you essentially just see a blinding star-like point of light.
You can't see the actual galaxy.
No, you can't see the spiral arms or the galaxy itself without highly specialized equipment blocking that central glare. But a Seyfert galaxy is slightly less luminous, relatively speaking. It is hosted in a spiral galaxy, much like our own Milky Way, but with an AGN operating at a, let's say, a lower gear.
So with the Seyfert, the host galaxy doesn't get completely blown out by the central glare.
Exactly. With a Seyfert galaxy, the beautiful swirling galactic structure, the spiral arms, the dark dust lanes, the regions of active star formation, it all remains clearly visible to our telescopes alongside the intensely bright core.
So it's not just a floating flashlight.
Right. It gives astronomers a much clearer context of the environment surrounding the black hole. We can see the neighborhood, not just the floodlight.
I love that. So imagine you're looking through a powerful telescope. You see this glowing, magnificent spiral galaxy, a pinwheel of billions of stars floating in the dark. At the very center is a blindingly bright core, the accretion disk of the supermassive black hole actively feeding. And then, over the course of just a year and a half, which is barely any time at all, you watch that blinding center suddenly dim to a tiny fraction of its original strength, while the rest of the galaxy around it keeps turning, completely undisturbed.
It's a haunting visual.
It really is. But a visual can only tell you so much. A picture might tell you a galaxy got dimmer, but it won't tell you the physics of why or how the structure around the black hole changed. For that, astronomers have to decode the light itself using spectral fingerprints.
Right, because we don't just look at photographs to understand what's happening. We rely on spectroscopy, which is arguably the most powerful tool in all of astronomy.
Period.
Absolutely. To understand the changing look aspect of this galaxy, we have to break down how we classify active galactic nuclei into type 1 and type 2.
Okay, for those of us who haven't played with a prism since elementary school science class, how does reading the light actually tell us what is happening near a black hole 1.3 billion light years away?
Well, think about Isaac Newton passing sunlight through a glass prism and seeing a rainbow. Spectroscopy is essentially the advanced version of that. When astronomers pass the light from a distant galaxy through a spectrograph attached to a telescope, it breaks that light down into its constituent wavelengths, creating a spectrum.
Okay, so a very detailed rainbow.
Right, but it's not a perfectly smooth, continuous rainbow. When you look closely, you see specific, distinct, bright lines at very precise wavelengths. These are called emission lines.
And these lines act as a barcode for the universe, don't they?
Exactly like a barcode. Every chemical element, hydrogen, helium, carbon, iron, has a unique atomic structure. When the electrons in these atoms are heated up by the intense energy of the black hole, they jump to higher energy levels.
They get excited.
Right. And when they fall back down, they release a photon of light at a very specific, unchanging wavelength.
Wow.
So by looking at where these bright lines appear on our spectrum, we know exactly what kind of gas is glowing in that distant galaxy.
That's incredible.
But the spectrum tells us more than just chemistry. It tells us velocity.
Oh, right. This is where the Doppler effect comes in. I think most of us understand the Doppler effect when it comes to sound.
Sure.
You know, you hear an ambulance coming towards you, and the siren sounds high-pitched because the sound waves are being compressed. As it passes and drives away, the pitch drops noticeably because the sound waves are being stretched out. But how does that apply to light?
It works the exact same way. If a cloud of glowing gas in space is moving rapidly toward our telescopes on Earth, light waves it emits get slightly compressed. We call this blue shift because the light is shifted toward the shorter, bluer end of the spectrum.
Okay.
And if the gas is moving rapidly away from us, the light waves are stretched out, shifting them toward the longer, redder wavelengths. This is redshift. Now apply this to a swirling accretion disk and the clouds of gas orbiting the black hole.
Well, the gas on one side of the black hole is rotating toward us.
Yeah.
And the gas on the other side is rotating away.
Right. Let's start with a type 1 AGN. When we look at a type 1, the spectrograph shows us two distinct types of emission lines: broad lines and narrow lines.
Broad and narrow.
The physical reality behind this is fascinating. The broad lines are created by gas that is swirling extremely fast, very, very close to the supermassive black hole in a region heavily dominated by the black hole's immense gravity.
So deep in the gravity well.
Yes. According to Kepler's laws of orbital motion, things closer to a massive body must orbit faster. We are talking about gas moving at thousands of kilometers per second.
Wow.
Because the gas is moving so incredibly rapidly, the Doppler effect severely smears the wavelength of the light it emits. The light from the gas moving toward us is heavily blue-shifted, and the light moving away is heavily red-shifted. When you combine all that light into one signal, it creates a wide, fat, broad peak on our spectrograph.
So when an astronomer sees a broad line, they know they are looking at incredibly fast gas deep in the danger zone, right next to the engine.
Yes, and the narrow lines in a type 1 spectrum come from clouds of gas that are located much further away from the black hole.
Where it's safer.
Where the gravitational pull is significantly weaker, yeah. The gas is moving much slower, maybe just hundreds of kilometers per second. Because the velocity is lower, the Doppler shifting is minimal, the light isn't smeared out.
So it's a sharper peak.
Exactly. It creates a sharp, tall, narrow peak on the graph. So a type 1 AGN shows both the fast, broad inner gas and the slow, narrow outer gas.
And a type 2.
A type 2 AGN shows only the narrow emission lines. The broad lines are completely absent from the barcode.
Interesting.
This means we are only seeing the slow-moving gas far away from the black hole. We aren't detecting the fast-moving gas right next to the engine at all.
Okay, hold on. To a layperson, classifying a galaxy as type 1 or type 2 makes total sense. Either you see the fast inner gas or you don't. But the universe rarely deals in just black and white.
Very true.
Astronomers have these micro measurements. We have intermediate subtypes sitting right in between, like type 1.2, 1.5, 1.8, and 1.9. I gotta say, arguing over a 1.8 versus a 1.9 sounds like splitting cosmic hairs.
Yeah.
Why does this micro-level classification actually matter to our understanding of how the black hole operates?
Because it reveals the thermodynamics of the engine shutting down. The intermediate types are where the taxonomy gets incredibly precise. They are ranked purely by how strong the broad emission lines are relative to the narrow ones.
Okay.
And astronomers look for very specific chemical signatures to make this judgment, particularly two specific hydrogen emission lines known as hydrogen alpha, or H alpha, and hydrogen beta, or H beta.
Let's break this down. Why focus on those two hydrogen lines specifically?
Well, hydrogen is the most abundant element in the universe, so its signals are the loudest. In the atomic structure of hydrogen, an electron jumping from the third energy level down to the second produces the H-alpha line, which is a specific shade of red.
Got it.
An electron jumping from the fourth energy level down to the second produces the H-beta line, which is a specific shade of blue-green. Here is the crucial physical difference. It takes significantly more energy from the black hole's radiation to kick an electron up to that fourth level to make H-beta than it does to kick it to the third level to make H-alpha.
So the H-beta line requires a hotter, more energetic engine to exist.
Precisely. So as an AGN starts to lose power, the environment cools down. It doesn't have the intense energy required to excite the hydrogen atoms to that fourth energy level anymore.
So what happens?
The broad H-beta line starts to fade away first. In a type 1.8 AGN, you can still clearly see one broad line, the hydrogen alpha line, because the engine still has enough juice for that. But the broad hydrogen beta line has become very weak. It's just barely hanging on.
It's like watching a city experience a rolling blackout. The most power-hungry industrial sectors shut down first, while the residential lights stay on a little longer.
That is a highly accurate way to view it, actually. As the temperature continues to drop, the power-hungry H-beta line vanishes entirely. When you show just the broad H-alpha line, you are classified as a type 1.9.
Just one broad line left?
Yep. If the engine cools even further and that final broad H-alpha line disappears because there isn't even enough energy to excite electrons to the third level, you've arrived at a type 2. The fast inner gas has gone completely dark.
Which brings us to the changing look identity of HE 1237-2252. This galaxy didn't just sit comfortably in one category, it moved through them.
Right. What's fascinating here is that shifting between these highly specific classifications reveals the real-time physical transformation of the space immediately surrounding the black hole. Historically, based on archival data, HE 1237-2252 was classified as a type 1.0 to 1.2.
So it was running hot.
Very hot. It had strong, clear, broad lines for both H-alpha and H-beta. The engine was roaring at high temperatures.
But then, when astronomers observed it in 2022, the spectrum had shifted all the way down to a type 1.8. The broad H-beta line had almost entirely vanished. The power-hungry sector of the gas near the black hole had effectively gone dark.
And the story didn't end there. By late 2024, observations showed its spectral lines had fully recovered.
Wow.
The broad H-alpha and H-beta lines were back in full force, returning the galaxy to a Type 1.0 classification. Now, over 150 of these changing-up AGNs, or cryogens, have been confirmed to date.
So it's not the only one.
No, they're usually found through repeat optical spectroscopy over many years, or by scanning large photometric surveys. But catching one shifting so dramatically and capturing the entire cycle of dimming and recovering in such a brutally short window of 18 months, that is a rare treasure for astrophysicists.
So we know the engine throttled down. We know the spectral fingerprint shifted, proving the gas physically cooled and then reheated. But how did humanity actually coordinate the tracking of this massive event? I mean, we are talking about something 1.3 billion light years away. You don't just point a single backyard telescope at it and call it a day.
No, absolutely not.
This required an astronomical stakeout across multiple wavelengths of light.
The coordination required to monitor an event like this is a massive logistical triumph for modern astronomy. Getting time on major space telescopes is incredibly competitive.
I can imagine.
You have thousands of astronomers writing proposals, waiting years for a few hours of observation time. But when an event like this happens, it triggers what are called target of opportunity protocols.
Basically skipping the line.
Exactly, allowing astronomers to essentially interrupt the scheduled programming of humanity's most expensive satellites.
So the initial spotting of this dramatic dimming happened in January 2022. It was detected using an instrument called eROSITA.
Yes. The discovery was led by an astronomer named Alex Markovits and his team at the Nicholas Copernicus Astronomical Center. eROSITA stands for the Extended Roentgen Survey with an imaging telescope array. It is an X-ray telescope in orbit, basically scanning the entire sky.
Let's talk about how an X-ray telescope actually works. Because it is fundamentally different from a ground-based optical telescope, isn't it? You can't just use a normal mirror.
You absolutely cannot. If you tried to use a standard curved glass mirror like the ones in the Hubble Space Telescope or ground-based observatories, the X-rays would just blast straight through the glass or be completely absorbed by it.
Because they have too much energy.
Right. X-rays carry far too much energy to be reflected at a direct angle. So to focus X-rays, astronomers use what are called grazing incidence mirrors. Think of skipping a stone across a pond.
Okay.
If you throw the stone straight down, it sinks. But if you throw it at a very shallow grazing angle, it skips off the surface.
So they build a telescope that essentially skips X-rays into a detector.
Precisely. They use nested cylindrical mirrors coated with heavy metals like gold or iridium. The X-rays enter the tube, skip off the shallow angles of the mirrors, and are slowly guided down into a focal point at the detector.
That is brilliant engineering.
It is. So eROSITA surveys the sky in soft X-rays, and when the team analyzed the data for HE12372252 from January 2022, they saw that the soft X-ray flux had simply collapsed compared to previous archival observations from years prior.
And once that alarm was sounded, the bureaucracy of space astronomy had to move at lightning speed. They triggered a global and orbital coordination effort to track the galaxy across the entire electromagnetic spectrum. They essentially aimed every lens humanity has at this one spot in the sky.
Pretty much. From late 2022 all the way through early 2025, they brought in an absolute arsenal of instruments for a follow-up campaign. In space, they didn't just rely on eROSITA. They brought in the XMM Newton X-ray Observatory, which is one of the most powerful X-ray telescopes ever built. They utilized the Swift Observatory, which specializes in rapidly pointing at transient events in X-ray and ultraviolet light. They also tasked the NEOWISE satellite, which maps the sky in infrared light.
And down here on Earth, they had ground-based optical photometry networks stepping in too, right?
Yes. Specifically, the LCO, the Las Cumbres Observatory, and the PROM-T telescope networks, as well as the ATLAS survey, which normally looks for near-Earth asteroids but sweeps the sky so frequently it's fantastic for spotting changing galaxies.
Why do they need all of that? I mean, why is that multi-wavelength approach so essential?
That multi-wavelength approach is non-negotiable for understanding black holes. A single telescope only gives you a tiny slice of reality. Different types of light tell you what is happening in physically different parts of the black hole's environment.
Oh, I see.
We established that the X-rays come from the very innermost region, the incredibly hot magnetized corona right next to the event horizon. Ultraviolet and optical light, the kind we can see with our eyes or standard telescopes, come from the main body of the accretion disk spreading outward. And infrared light comes from massive clouds of dust and gas located much further out, essentially measuring the ambient heat generated by the inner engine.
Which leads us to a massive discrepancy in the recovery rates they observed. This is a core piece of the mystery. The dimming wasn't just happening in X-rays, the infrared brightness had dipped significantly as well.
Yes, it did.
But when the black hole started to reignite, the different types of light didn't come back at the same time. The timeline of the recovery was highly stratified.
Very stratified. The highest energy light from the innermost region, the X-ray flux, bounced back incredibly quickly. It recovered in a mere 3 months. The engine sparked back to life.
3 months is nothing.
Right. But the optical, the ultraviolet, and the infrared bands, the light coming from further out in the system, took a sluggish 3 years to fully recover.
So what does this all mean? Why would the X-rays snap back in 3 months, while the infrared or the UV light takes 3 years? If the engine turns back on, shouldn't the whole thing just light up at once?
It comes down to the sheer physical distance of the structures involved and the hard speed limit of the universe. The speed of light. Think of it like a massive industrial stovetop.
Okay, I like this analogy. Walk me through it.
The X-rays are the red-hot, glowing electric coils in the center of the stove. They are the direct source of the extreme heat.
Got it.
The optical and UV light represent a heavy iron pan sitting on those coils. The infrared light represents the ambient air warming up in the kitchen. If you crank the dial and turn the stove on, the electric coils, the innermost corona, get hot and glow almost instantly. The X-rays flare up.
Right.
But it takes time for that heat to physically conduct through the heavy iron pan. It takes even longer for that heat to radiate out and warm up the entire kitchen.
So it's literally a delay in cause and effect across the physical distance of the disk.
Exactly. When the central feeding process restarts, the innermost region gets hot instantly, generating X-rays. But the signal that the engine is back on the intense radiation heating the outer disk takes months to physically travel from the center to those outer edges. The ultraviolet and optical light take time to ramp back up.
And the infrared light takes even longer.
Because the infrared light originates from a massive donut-shaped structure called a dust torus that surrounds the entire Aegean system, located light years away from the center.
Oh, light years?
Yes. The X-ray and UV light have to travel from the black hole, traverse that vast distance, hit that cold, distant dust, heat it up, and then the dust re-emits that energy as infrared light. That light travel time creates a natural delay, a sluggish, multi-year echo of the central event.
Okay, I have to play the role of the skeptical observer here for a second.
Please do.
We are talking about complex thermal waves, magnetic reconnections, and light speed time delays across accretion disks. But couldn't there be a much simpler, more intuitive, everyday explanation for why something far away might suddenly look dim to us?
Science requires testing all hypotheses, especially the simplest ones. Occam's razor. What is the alternative theory?
What if a massive rogue dust cloud simply drifted across our line of sight?
Oh, the dust cloud theory.
Yeah. Space is full of dust, gas, and stellar debris. The galaxy is rotating. What if an incredibly dense clump of material just happened to pass exactly between our telescopes on Earth and the center of HE 1237 2252? It would be like someone holding their hand over a flashlight.
Right.
The flashlight didn't turn off, it's just physically blocked. Could an obscuring cloud explain the dimming we saw?
It is a vital question to ask. In fact, in the early days of studying changing look AGNs, before we had such robust multi-wavelength coordination, obscuration by a passing cloud was actually the prevailing theory in astronomy.
Makes sense. It's simple and mechanically sound.
However, the multi-wavelength data we just outlined completely dismantles this dust cloud theory for this specific event. We can definitively prove the flashlight actually turned off.
What's the smoking gun that proves it wasn't just a rogue cloud acting as a filter?
There are two major pillars of evidence, based entirely on how different wavelengths of light interact with physical matter. Reason number one lies in the X-ray data from eROSITA and XMM Newton.
Okay.
If a massive dust cloud had passed in front of the black hole, we wouldn't just see a clean, uniform drop in the overall amount of X-rays. We would see distinct, telltale signs of absorption.
What does X-ray absorption actually look like in astronomical data?
Think about a medical X-ray at the doctor's office.
Sure.
The X-rays pass easily through your soft tissue, which is why your skin and muscles look transparent on the film. But the X-rays are absorbed by the denser calcium in your bones, casting a shadow.
Right.
In space, dust clouds act similarly. They are highly effective at blocking lower energy or soft X-rays, but they are relatively transparent to higher energy or hard X-rays, which just punch right through.
So if a cloud was blocking our view of the black hole, the spectrographs would have recorded a massive drop in the soft X-rays, but the hard X-rays would have mostly remained steady.
Exactly. The spectrum would look skewed, it would look artificially filtered, but that is not what the observatories recorded. They saw a uniform collapse across the board. Soft X-rays, hard X-rays, all of it vanished simultaneously. The X-rays weren't being filtered by a cloud, they simply weren't being produced.
No. The Stoth coils were actually turned off.
They were turned off.
What is the second reason?
Reason number two is the infrared data from the NEO-WISE satellite. We talked about how the distant dust torus generates infrared light by absorbing energy from the center. Think about what happens if you shine a tremendously bright, hot spotlight onto a thick, dark curtain.
Okay, shining a spotlight on a curtain.
The visible light doesn't just disappear into nothingness. The curtain absorbs that energy, heats up, and radiates that heat away.
It essentially becomes a giant thermal blanket.
Exactly. In space, if an active black hole is shining intensely behind a massive rogue dust cloud, the dust in that cloud absorbs the extreme optical and ultraviolet radiation. It gets hot, and it glows brightly in the infrared.
So if a cloud moved in and blocked the visible light, the infrared brightness we detect from Earth should have actually stayed steady or even spiked, because the cloud itself is catching all that heat and glowing.
Exactly. The infrared output would remain high because the hidden engine is still pumping energy into the obscuring cloud. But NEO-WISE showed us the exact opposite. The infrared brightness dropped significantly right alongside the X-rays and the optical light.
The flashlight wasn't blocked. It genuinely lost power.
The conclusion is inescapable. Because both the X-ray spectrum collapsed without the specific signatures of absorption and the infrared ambient heat dropped, this was an intrinsic change. The black hole was genuinely producing less energy. The engine itself was failing.
Which brings us to the ultimate question, the thermodynamics of the void. If nothing was blocking our view, what actually happened inside that plasma accretion disk to cause a supermassive black hole to suddenly lose its appetite?
That is the million-dollar question.
Right. What physically causes an engine light months across to fail in 18 months and then restart?
This is where we reach the cutting edge of modern theoretical astrophysics. The leading explanation for what happened inside HE 1237-2252 involves the propagation of cold and warm fronts traveling through the accretion disk itself.
Are we talking about weather patterns on a galactic scale?
In a fluid dynamic sense, yes. We have to stop thinking of the accretion disk as a solid, flat dinner plate. It is a highly volatile, fluid, turbulent plasma. The dominant theory suggests that a local instability, likely related to the magnetic fields that provide the friction, a phenomenon called magneto-rotational instability, triggered a sudden collapse in the heating mechanism.
Okay.
This created a cooling wave that rapidly traveled outward through the inner regions of the disk.
Mechanically, what happens when a cooling wave hits superheated plasma moving at relativistic speeds?
Well, as this cooling front propagates, it drastically lowers the temperature of the plasma. And when that happens, the physics change dramatically. Cooler plasma means less turbulent magnetic friction. Less friction means the material isn't radiating as much extreme energy. Crucially, as it cools, the vertical height of the disk shrinks. It deflates from a puffed-up, donut-like shape into a thin, razor-flat disk.
Like a balloon losing air.
Exactly. And this thin structure is incredibly inefficient at feeding material inward. The physical flow of gas into the innermost corona chokes off. The cooling wave temporarily suppresses the entire disk's energy output.
That explains the 18-month drop. The cooling wave swept through, deflated the disk, choked the fuel line, and shut the X-ray corona down.
But a black hole's gravity is relentless. The system will always attempt to reestablish equilibrium.
Because the mass is still there.
Yes. As the material continues to pile up in the deflated disk, the density increases. Eventually, the friction must reignite. This triggers a warming wave, a wave of heating that slowly propagates back through the material.
It pushes back.
Right. This warming wave gradually restores the extreme temperatures, puffing the disk back up, reigniting the intense magnetic friction, and forcefully pushing material back toward the event horizon. The brilliant luminosity is slowly restored.
And astronomers actually saw hard evidence of this reignition phase, didn't they? As the black hole roared back to life in late 2024, researchers detected something highly distinct in the spectral data.
They did. As the galaxy returned to its Type 1.0 status, meaning the broad emission lines returned, the researchers detected a highly distinct double-peaked pattern in the hydrogen emission lines.
A double-peak pattern.
Mhm.
What does that imply about the geometry of what we're looking at?
It is a beautiful geometric clue. When you see a single broad peak, you are generally looking at a turbulent, messy cloud of gas swirling around. But when you see a distinct double peak in an emission line, it usually means you are looking at a highly organized, rotating ring of gas. Yes. One peak is the side of the ring rotating rapidly toward you, which is blue shifted. The other peak is the side rotating rapidly away, which is red shifted. There is a dip in the middle. The implication here is stunning. It hints that as the inner corona of the black hole suddenly flared back to life, its intense X-ray radiation reached out into the darkness and illuminated a brilliant, ring-like structure of gas residing just above the disk.
Building on that, it sounds exactly like turning on a stadium spotlight in pitch blackness.
Exactly like that.
You flip the switch, and suddenly the intense beam of light catches the curved rim of the bleachers. We only saw the ring of gas because the central light finally turned back on to illuminate it.
The recovering corona acted as a massive cosmic flashbulb, revealing the hidden architecture of the space immediately surrounding the black hole. And this specific discovery, the sudden appearance of this double-peaked ring, ties directly into a much broader, long-standing debate currently raging in astrophysics.
Regarding the fundamental nature of that broad-line gas we talked about earlier.
Yeah.
The fast-moving gas that creates the Type 1 signature, why is there a debate about it? Don't we know it's just gas orbiting the black hole?
The argument is really about permanence and origins. Is the broadline gas region a permanent, massive structural reservoir of material that just sits there, orbiting the black hole, essentially waiting to be illuminated?
Okay.
Or is it not a permanent structure at all, but rather a dynamic wind?
A wind, like being blown away.
An outflow of gas that is continuously being blown off the surface of the accretion disk, entirely dependent on the black hole feeding above a certain threshold.
Oh, wow. That is a massive physical distinction. Are we looking at a permanent physical structure like a belt of asteroids?
Yeah.
Or a temporary weather phenomenon like a hurricane created solely by the heat of the engine?
Right. And if we connect this to the bigger picture of how galaxies evolve, you can see why HE 1237-2252 is so incredibly important. If the engine drops below a specific power level, does the wind just stop blowing, causing the broadline region to literally cease to exist?
And then when it turns back on, does it have to blow a brand new wind?
Exactly. This galaxy serves as a real-time laboratory to test these exact models. By watching the broad lines vanish as the cooling wave hits, and then reappear with that double-peaked ring signature as the warming wave restores power, researchers can measure exactly how the gas reacts to the turning off and turning on of the central engine.
It's like turning the machine on and off to see which parts move.
It provides the hard observational data needed to finally resolve these theoretical debates about how black holes interact with their host galaxies.
It is just phenomenal to think about. We set out to understand the scale of a changing look AGN, and the journey we just took is staggering.
It really is.
We have tracked a supermassive black hole 1.3 billion light-years away. We watched it mysteriously dim its X-ray output by a massive factor of 17 in just 18 months, effectively choking off its own fuel line. We saw a massive coordinated network of Earth and space-based telescopes, eROSITA, XMM Newton, NEOWISE, Atlas, all point at the same spot to prove beyond a shadow of a doubt that it wasn't just a passing dust cloud.
Definitely not a cloud.
It was an intrinsic, catastrophic failure of the black hole's feeding mechanism. And finally, we mapped out how fluid thermodynamics, cold and warm waves rippling through a relativistic plasma accretion disk can temporarily starve a black hole, only to watch it slowly come back to life, acting as a flashbulb to illuminate a hidden ring of gas in the process.
And this event is a loud, clear signal to the astronomical community. The researchers who published this detailed analysis have a specific, urgent call for the future of astrophysics. To truly unravel the physics of these changing-look AGNs, astronomy needs more high-cadence optical and UV monitoring campaigns. We cannot rely on archival data taken years apart.
We can't just check in every decade.
Exactly. We need telescopes checking in on these active galaxies, frequently not once a decade, but constantly week after week.
We need to watch the movie, not just look at isolated Polaroids from a family album.
Precisely. If we monitor them continuously, we can catch these cooling and warming waves as they initiate in real time. We can map the propagation of the thermal fronts across the accretion disks and finally understand the exact triggers that cause these supermassive engines to stall out.
Yeah, and that leaves us with a final thought I want you, listening right now, to ponder. When you look up at the night sky, it is so easy to fall into the trap of thinking of the universe as a slow, static painting, a quiet, unchanging backdrop to our frantic human lives.
But it's not.
No. HE 12372252 proves that the cosmos is fiercely, violently active. If a supermassive black hole, an object containing the mass of millions of suns, anchoring an entire galaxy, can effectively turn off and on in the time it takes a human being to finish a college degree, it begs a massive question.
A very exciting question.
What other immense, rapid cosmic engines are throttling up or down right now, hidden in the dark, just waiting for us to finally point a telescope in their direction?